hello, 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 mic check, hello, hello. एक चालू करतो बोल. हॅलो माईक चेक. हॅलो हॅलो. ओके. हॅलो. हॅलो हॅलो माईक चेक. हॅलो हॅलो. हॅलो हॅलो माईक चेक. ओके.
Hello, hello,
हॅलो हॅलो.
hello. Mic check.
थांबा दोन. हॅलो हॅलो माईक चेक. हॅलो हॅलो. ओके. हॅलो.
Hello, hello. Mic check. Hello, hello. नको.
Testing. Hello. Is that good? Yep. Okay. Yeah. Hello. Hello. Hi. Oops.
काय सांगायचं
There.
माईकच्या वर लावायचं थोडा.
yeah, just put it,
Want it closer?
slightly above.
Okay.
Slightly above, yeah.
Hello. Testing. 1, 2, 3. Testing.
ओके.
Hello. Hello. A Quark's life. A brief history of the universe from a new perspective. That's too loud, isn't it? I'm speaking very softly and
2 मिनिट फक्त.
Yeah, you can just send her. You can sit.
Okay.
Sorry, it's just.
Hello? Hello, testing, hello?
One sentence.
A Quark's Life, a brief history of the universe from a new perspective.
Aniket,
Is that working okay? A Quark's Life. My name is Jane Charlton. I'm from Penn State University. And I'm glad to be here today. A brief history of the universe from a new perspective. I'm going to tell you a story today. A story as old as time.
Hello, check.
Literally.
you're getting hints of Carl Sagan.
A story of the Big Bang. Oh, well, absolutely. I told you I was doing Carl Sagan, not Neil deGrasse Tyson. I don't know how to do Neil deGrasse Tyson. That's not my style. But,
We've grown up on that. So.
mm-hmm.
Aniket,
So do you happen to have Jairam's number? Jairam's number? So Jairam and Jane overlap the coordinate?
Or did
We
we,
wanted to just have.
sure.
am I supposed to turn it off yet?
Can I have?
Yeah.
I have his email address, but I don't have his number,
Yeah.
and probably WhatsApping is a faster way.
Sure. I can get
I think we didn't actually quite overlap.
Is it?
I think we didn't overlap, but we knew each other pretty good. Yeah. I don't remember if he was after me or before me.
So you
87.
Thanks.
Hello, hello. 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 Mic check. Hello. Mangesh. Hello. Mic check.
हे आता समोर जो वापरण ना तेव्हा ते आवाज वाढवायला सांगतो मी वाटलंच तर जो माईक घेईन ना तेव्हा आता 3 माईक सांगितलेत ना आपल्याला हे ना ठीक hello mic check hello hello mic check hello mic check hello mic check hello hello mic check hello mic check okay
Okay. Good evening, everyone. We would like to welcome you all to the Inter-University Center for Astronomy and Astrophysics. But we are also, we regret announcing a short delay in the starting of the program. So we'll be starting in 5 minutes. So please, feel comfortable in this lovely auditorium, and we'll get back to you very soon.
लागला तर हां तुम्हाला दिसेलच इथून तसं पुढे घेतले त्यामुळे दिसत नाही हां चालेल.
Okay, good evening everyone. I request those who are sitting behind, so please come ahead here because these seats are completely vacant here. I request you to please come ahead. Yes. Sure. Sure. So again, I am requesting you to come ahead because this lecture is kind of a play, which whenever you are in a, whenever you want to see a play, you basically do not sit behind, you sit ahead. Okay, so yes, please do come ahead.
I'm the speaker, and I'm going to cry if you don't move forwards.
Okay. Okay, thank you so much. Yeah.
Good evening again. I'm Samir Dhurde, and I again welcome you all to a special event, which is part of a special conference which is going at IUCAA. This is a part of the series of the Chandra public lectures, which are hosted in the Chandrasekhar Auditorium by IUCAA very regularly. So we are in the recent years, we've been doing it once a month almost, or sometimes more, on some Thursday evenings. So if you do not have that noted down, just please do that. And we also announce them regularly on our social media platforms. So just look up IUCAA Science Outreach or Public Outreach, and you'll keep getting our regular updates. So today's event is part of the conference, as I said, which deals with baryons. It's called Baryons Beyond Galactic Boundaries. We have a huge number of people, colleagues from all over the world who deal with these heavy particles that we are all made up of. But then how much do we know about this? How much is the popular knowledge? Well, I don't know how much it is, but definitely with this talk, we hope to have a significant increase in the understanding of how these particles came to be, and some things which are also part of these particles. So these would be quarks, and we have a special speaker here who will be guiding us through the life of a quark through a very beautiful and engaging talk, or rather, let's say, a unique talk. To introduce her, I will invite on stage Mr. Anand Narayanan from IIST, and then
Good evening, everyone. It's my pleasure. I should say I'm super thrilled to introduce the speaker for today evening's public lecture. I'm probably more thrilled than the speaker herself, and that's because I have the rare privilege to be a student, a doctoral student of Professor Jane Charlton, who is from Pennsylvania State University. In 2008, I completed my PhD under her, where we looked at the evolution of galaxies and gas associated with galaxies over cosmic time. So as a student of Jane, I've learned a lot. I learned the art and science of doing research. I've learned the art of science of telling stories about science. I've learned how to be a good teacher for students. I've learned how to be a mentor. A lot of things I owe to Jane. So when IUCAA asked me whether, I'm also attending the Baryons Beyond Galactic Boundaries conference, and when IUCAA asked me whether I would like to introduce Jane, I didn't have much time to reflect on it. I just said yes, okay, because I truly consider it as an honor to introduce my own supervisor. So thanks IUCAA for the opportunity. Let me just say a few things about Jane. Jane grew up in Pennsylvania. That's where she did her schooling. And for her undergraduate work, she went to Carnegie Mellon University. And from there, she went to University of Chicago for her PhD, where she worked with David Schramm and Mike Turner on a certain domain of cosmology and evolution of the universe. And she completed her PhD at the age of 22. And from there, she went on for her first postdoctoral position at Cornell University under Edwin Salpeter. So those of you who know the history of astronomy, Salpeter played a prominent role. He was a central figure in understanding how stars produce their energy through nuclear fusion reaction. And then one other important thing is that while she was a grad student at University of Chicago, the first year that she was a grad student at University of Chicago, that's when Subramaniam Chandrasekhar, who was a faculty at the University of Chicago, won the Nobel Prize. So while I was a grad student at Penn State, Jane has told me very interesting stories about Chandra, and now this public lecture is happening in an auditorium that's named in honor of Subramaniam Chandrasekhar. So yeah, so she did her first postdoc at Cornell University, as I mentioned, with Ed Salpeter. And then she did her second postdoctoral position at the University of Arizona. And after that, she moved on to Pennsylvania State University in the year 1992. And since then, she has been a part of the faculty at the Department of Astronomy and Astrophysics at the Pennsylvania State University, where she has mentored several generations of students, and I happen to be one of them. Jane also has a very keen interest in education and public outreach. She has done a lot of work in that particular domain. One important thing that I should mention is that Jane is the architect, the chief architect of introductory astronomy course that starts from the coordinate systems and goes all the way to cosmology, the birth of the universe. It's an introductory astronomy course. She has designed and built this introductory astronomy course that is taken by more than 10,000 students worldwide. Every year, more than close to 4,000 students register for this course. And the reason why there are so many subscribers to this course is because this course is not a typical lecture-oriented course, but the course is a immersive video game with characters into it. And through this video game, one learns about the basics of astronomy and astrophysics. So Jane has always been interested in the storytelling aspects of science, and which is why this course also happened. And this course is now taken not just by students of Penn State, but students from universities across the globe. And she still handles that course. Jane has won several awards. Just to mention a few, she won the Presidential Award for Faculty Member who has the best combination of research, teaching, and service to the university and the community. And she has also won another prestigious award for integrating information technology into teaching. So with these few words, it is my honor and privilege to welcome Professor Jane Charlton to this lecture.
Thank you, Anand. You're welcome, Professor Jane. And I'll move over to the other side of the stage.
Okay.
Thank you. All good.
Yeah. You may take your seats. Okay, so not only did was I there when Chandrasekhar won the Nobel Prize, but I almost ruined his day that day. Normally we had a regular seminar on that day of the week, and the graduate students were charged with making the coffee for that occasion. And I was a new student, and so this was my first turn at making the coffee. And you see, I had never made coffee before. And suddenly, just before this was happening, I was told that not only was I making it for the seminar, I was making it for a huge party that was being held in honor of Chandrasekhar's Nobel Prize, which he had been awarded that very day. And we found ourselves, there was another student with me who was equally unable to make coffee, and we had no filters for the coffee machine. So we thought paper towels are similar to filters. They're not. They're not. We did manage to scramble and fix the situation so that the party went off without a hitch, so that was a good thing. So I'm very excited to be here and have an opportunity to share this story with you. It really is a story of a quark's life, and it's a story about really how amazing the universe is, and not just how amazing the universe is, but how equally amazing the human brain is. So we don't really know how something becomes conscious. Human consciousness is one of the biggest mysteries that we need to understand. But presumably it has to do with the particles inside our brains and the way that they interact with each other. And especially when we think about, new ideas in quantum mechanics and everything, you start to think, well, does each of the particles in my brain have a little bit of consciousness that combine together to make me conscious? And so that's just like a way of thinking of things, not a scientific idea or anything, but it is sort of what gave rise to the idea for this talk, where I want to talk about 3 tiny particles called quarks in my brain. Their names are Hader, Lena, and Jai. And I want to tell you about when they were born and what path they've taken through the universe in order to be here today. And what I'm going to tell you is fanciful, but also possible, that this is indeed the path that these quarks have taken. So hopefully it will be thought-provoking. And just for the purpose of this hour, I've asked the quarks to leave my brain and take human form, and they're sitting over here, right here. Yes, yes. So would you introduce yourselves?
Hi all, I'm Jay and I'm the Dawn Quark.
Hi, I'm Lena, and you will find me in red here.
I'm Haider in this play, and I'll be the green quark. Obvious from the dress colors, I hope.
Okay. So we're going to begin with a little conversation between these 3 quarks in my brain. They're bound into a proton, and they're living in the right frontal lobe of my brain. Please go ahead, Lena.
She's going to stand here and talk about this boring stuff now.
Yeah, another boring day. What is the point? Blah, 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 blah.
Hey, but don't you remember all the places that we have been? don't you know how lucky we are to be here today? And see, you're also upsetting Jane because she's losing all the enthusiasm that she had about astronomy when she was young.
So, our universe is expanding. And when I say that, what I mean is that the galaxies in the universe are all moving apart from each other. A galaxy is a city of stars, and our sun is one of 100 billion stars in our own city of stars, the Milky Way galaxy. There are many other galaxies out there as well, and we'll see images of some of them later. But each of the blue dots in this little movie are meant to illustrate a galaxy. And if we think of our universe as two-dimensional, like the surface of a balloon, rather than three-dimensional, so that we can just visualize it, you see how every single galaxy is moving apart from its neighbor, getting further and further apart with time. And it's not that the galaxies are moving away from a center on the balloon, but rather it's the space of the universe itself that is stretching. And that is what is giving rise to this expansion. It's as if space is being added to the universe at every moment, at every location. Where is that space coming from? It's coming from something that we really don't understand or visualize, perhaps from other dimensions. And so it's really quite an amazing thing. Another amazing thing is if we trace back in time from the present moment, we can look at that on the right-hand side here. We see that all of the galaxies are moving towards one another. If we keep going back, it's 13.8 billion years ago that all of the material that makes those galaxies would have been in a region smaller than the size of the head of a pin, which means that the universe was very different then at the beginning of the Big Bang expansion. And back then, the universe was very hot, very dense, with all of the matter just smashed together like a black hole, but not a black hole just at a point, because around that black hole, there was even more matter that was equally dense. And conditions were very, very different than they were today. And because it was so dense and hot, the energy that was available was tremendous. And there was a sea of radiation, a sea of light, of very high energy. And the light was carried in the form of a particle called a photon. Okay. And these photons had such high energy that anything could happen. And photons could make a combination of a particle and its opposite charged antiparticle. That is through really the most famous equation in physics, E equals mc squared, Einstein's general relativity, where energy can convert to mass and mass can convert back to energy. So that's exactly what was happening, that all different kinds of particles, little small mass particles, big mass particles, they were all being made with their corresponding antiparticle. They'd travel a certain ways, and before you know it, they'd collide in those highly dense conditions with a partner, and they'd disappear again, or annihilate, and make another burst of radiation. So that's what the universe was like 13.8 billion years ago. Let's have a look. So we see the solid particles, those are the particles and their counterparts, the antiparticles, and you see little smaller white dots. The white dots are the photons of light. And sometimes the photons just generate a particle and an antiparticle, and then sometimes those collide with each other and give rise to a burst of light. We have the universe that we have today because for some reason, we have a little understanding of the reason, but not a very solid one. For some reason, there were just a slight bit more of the particles than of the antiparticles. The universe was expanding, and the collisions that would annihilate them stopped happening. And when that was all done, we were left with just the particles. So that is why we are here. So most of the particles annihilated with antiparticles, but Hadr survived.
Yeah, I remember the day I was born. There were so many particles around me, and they were annihilating with so many antiparticles, so many bursts of radiation. You know, and there were so many new particle-antiparticle pairs were coming up out of nowhere. It was amazing. I moved close to an anti-up quark, and I almost hit it. But then a top quark came by and knocked it off its course. So I got saved.
Yeah, I remember that. It was all happening so fast, but you are right. We all survived this.
So our universe today is made of only 4 kinds of particles. You are made of only 4 different things that are indistinguishable from each other. Our sun is made of those same 4 things. If there is an alien alive on a distant galaxy, no matter what kind of a creature it is also made of those 4 things. Those 4 things are up quarks, down quarks, and electrons. Actually, it's just 3 things. Why did I say 4 things? 3 things, up quarks, down quarks, and electrons. But in the early universe, when there was so much energy and anything could happen, all of the 30 different kinds of particles could be made. And we can still make them if we generate high energies in particle accelerators. So it's worth just telling you about them. And these are the only things that exist in the way of regular baryonic matter. There are 6 different kinds of quarks, the 2 common ones, up quarks and down quarks. And then there are very unstable ones that don't last very long, so we don't see them very much. Charm, strange, top, and bottom are the names of them. To go with each of those, there can be an antiparticle, but as I said, those all disappeared. So there was an anti-up, an anti-down, an anti-charm, anti-strange, anti-top, and anti-bottom. So that is half of this grouping of fermions. There are 12 types of quarks and antiquarks. And then there are lighter particles called leptons, the electron being the famous one of those. Electrons, muons, tauons, and then neutrinos, electron neutrinos, muon neutrinos, tau neutrinos. So the sun generates neutrinos in its nuclear reactions, and we can detect those and figure things out about them. And then there are also very rare anti-leptons that can exist. Okay. In addition to these particles over here called fermions, there are particles called bosons, and those bosons carry the 4 forces. A photon is an example of a boson, and a photon carries the electromagnetic force. There's also gravity and a graviton, which gives rise to gravity waves, which I know a lot of people here at the Institute work on that topic. So they're gravitons, and then Strong force is carried by gluons from place to place. And it's actually gluons that are going to hold these three together into the proton. And then there's a weak force, and that's carried by W and Z bosons. So that's all the different kinds of particles that we have. But we're talking about these three. As we said before, we have our blue down quark, our green up quark, and our red up quark. And they got together. So tell us about that, please.
Do you remember when we got together?
Yeah, I wanted to be different. I wanted to find an anti-quark and be a part of a meson. But then I saw you two, and the force was strong, and we were joined.
Yeah, but it isn't so bad to be part of a proton. So for a tiny fraction of a second, I was with Edna and Jane, but they were two down quarks in a neutron. But then a photon came and it knocked us apart. So
Was Edna more pleasant than Lena?
Hey, you should be nicer. You couldn't be a proton without me.
So these three are bound together into a proton, and that's where they've stayed all this time. They are held together by the strong force through the exchange of gluons between them. And the thing about gluons and the strong force is that it holds together particles of different colors. That's why they have to be three different colors. What I mean by that is you're all aware of magnetism, which holds a positive and a negative together, right? Those are opposite charges. In the case of the strong force, you need the three colors to cancel out and make white, and that's why the strong force works on the three particles. So here's a little video showing what that must have been like when they joined together. You see the green, blue, and red, and you see the universe expanding, and that makes it possible for these groupings to join together into a unit, which you see in white. And at that time, both protons and neutrons were forming. About 6 times more protons than neutrons. A proton is a positively charged particle, which consists of 2 ups and a down. A neutron is neutral, and 1 up cancels with 2 downs. So that's the way that works. Okay.
So we became a proton. And I remember seeing some of the other protons join with neutrons. We tried a couple of times.
yeah, but then we got knocked apart. We had been around for about 100 seconds then, if I recall.
And about 1/6 of the protons ended up in helium atom, but we didn't.
I remember now. I was glad. I wanted to be just the 3 of us.
Okay. So this process is called nucleosynthesis because it's the process that makes nuclei of helium. And everything I've talked about so far here, everything that happened to them happened within 100 seconds after the expansion begins. Now don't worry, the rest of the talk is not going to take that long for every 100 seconds of the 13.8 billion year history of the universe. It's just that a lot of important stuff happened at the very beginning there. And the key is the expansion of the universe where things are cooling, less energy is available, and particles that try to join together, they don't get knocked apart anymore. Okay. So basically at this time, at 100 seconds, all of the neutrons that were around, all of them got bound together with protons into helium. And 25% of the mass of the universe got converted to helium at that time, and the rest was left as hydrogen. We can see that depicted here. Here we see all of our hydrogen, all of our protons, and we see 2 protons joining together with 2 neutrons to make these green particles, which are larger in size, depicted here, and those are the helium nuclei. So that is nucleosynthesis. But as they said, Hadr remained in the hydrogen nucleus. So after a very long time went by, they just kind of flew around through the universe, something happened.
But then she joined us.
Yeah, but it was such a long time. It was just the 3 of us. I believe it was like 300,000 years, 3 lakh years.
Ellie was something, wasn't she?
She was just an electron.
Yeah, Lena wasn't very fond of Ellie, honestly. So this process is called recombination. The idea is that an atom is made of the nucleus, which is positively charged, and surrounding electron that is negatively charged. But the electron can't bind to a nucleus when there are photons flying all around with high energy knocking it apart. So it took 300,000 years for the universe to expand and cool enough that the electrons could join in. Something very, very important happened then, at that time. We're going to have a look here. And so you see the helium and hydrogen nuclei in gold and in green, and in red are the electrons. You see the electrons start to circle around the nuclei. 2 electrons join each helium, 1 joins each hydrogen. In the white particles, notice the white particles, those are the photons flying through the universe, and they keep colliding with things. You see at the beginning of this movie, and then they change their direction. That's like a fog when protons collide and change direction. That's what's happening when it's foggy outside. And so it takes more expansion for the spaces between these atoms to be large enough that the photons can just get through. The electrons joining, that was very important for that, because that made the atoms more compact than the electrons flying around all free. And that lifted the fog. The universe became transparent at that point. And so they combined with the electron, and their proton became the nucleus of a hydrogen atom. So how did you really feel about this with Ellie?
Because of her, everything changed for the better.
Well, suddenly we could see the light, quite literally.
Jean calls it the cosmic microwave background radiation because the photons of light were free to travel through space once the electrons like Ellie had joined nuclei like us.
Photons started to zoom through space at the speed of light just to get away from Eli.
Wow, okay. Wasn't a very welcoming environment for poor Ellie. So the fog lifted, and when that happened, each photon was moving in a certain direction, and it kept moving in that same direction. Oh, there's one now, and there's one coming from there. I can't really see them, but when we used to have like old television sets, the static on the TV, part of that was due to the cosmic microwave background photons. They can be measured and detected, and they've come from the far reaches of the universe through the emptiness of space to tell us about the beginning of the universe and how things were then. When we see them today, they're cooled to a temperature of 2.73 degrees Kelvin, where 0 is the lowest temperature that can exist. The map here actually looks like it's really bumpy. Actually, the temperature is the same for all these photons within a fraction, a very tiny fraction of a degree, but they are varying in temperature just a little bit, and that is a map of the sky showing that there are certain hot spots and certain cool spots in the universe. And those hot and cool spots, they were super important because that determined where the particles started to collect. And those particles collecting, that's what ended up forming the stars that are so important for us to be alive today. So there was a little bit of regret, though, right then, wasn't there, folks?
Yeah, maybe it was because of her that we were left out.
Lena, you have always blamed her for that. All she did was orbit us.
Oh, come on. Are you two fighting about it again? No, we were not part of the first stars. But if the first stars hadn't existed, then we would not have been here, where we are today.
It was the radiation from those first stars that ionized us and drove Ellie away.
And don't you remember how beautiful they were?
So somewhere before 1 billion years into the process, the first stars form. And the first stars were a little different than the stars today. They were about 200, 300 times more massive than the sun. And because they were so massive, when they ended up using up all of their fuel, they couldn't stand up against their own gravity, and they collapsed and collapsed further and collapsed further and became black holes. And so, folks, you would have been in a black hole if you had been in one of the first stars, and you really wouldn't have a very exciting life there. So I think it's okay.
That is true. And then one of those stars made a black hole in the center of a big concentration of dark matter.
It was really long time, several billions of years.
Hey, but then something special started to happen. We were drawn in with lots of other protons and neutrons.
And we were swarming about, and eventually.
Sure. We were part of this very thin disk of the Milky Way galaxy.
So that was that. They came in to the Milky Way galaxy. We use computers to simulate what happens with gravity. As soon as that cosmic microwave background was produced, as soon as those photons started to travel freely, gravity was free to begin to do its job. And gravity attracts one particle to another. And then if there are two particles, they're more likely to attract a third, and then a fourth, etc. And structure grows and grows. And it is a slow process. Gravity is not a very strong force, but it has time working in its favor. And it has billions of years. And over the billions of years, little pieces came together to form bigger and bigger pieces. I'm going to play this again and describe it, so, but it's just giving you an idea that our computers can calculate the gravity between every particle and every other particle and figure out how fast they should move in what directions. And lots of astronomers use these kinds of computer calculations to figure out how the universe changed with time. And so our Milky Way galaxy was actually made very early on relative to a lot of other galaxies. It's an old galaxy. It's been around for quite a while, which has interesting possibilities of maybe life forming in our galaxy many billions of years ago around a star other than the sun. So just coming down. So this is what the Milky Way galaxy is. It's called a spiral galaxy. It didn't actually have a collision like this that you're seeing at the end of this visualization. It's just the best visualization that I could see. It's called the fire simulation. And we're going to have another look. So starting out, we're just going to see a few small particles, and they're coming together, and sometimes it'll fly by, but then they're pulled back by gravity again. Because of this early galaxies that formed a long time ago, they don't look like galaxies today. You see how this looks messy? That's the way early galaxies look, and we can actually look back in time at the light coming from the distance and see that that's the way that galaxies look. So they were smaller than galaxies are today. But this is about halfway through the history of the universe here that we're seeing in the simulation. And we see a well-formed galaxy already there. And we see little dwarf galaxies, they're called, kind of crashing into it. They can make a big stir. When a dwarf galaxy collides with a bigger galaxy, it can make new stars form. And in fact, our sun formed when that happened, when a galaxy called the Sagittarius Dwarf Galaxy, which we still can see in our halo today, crashed through the disk of our galaxy at about 8 billion years into the history. That's when our sun and a bunch of other stars formed. So that can be a very important part of the whole process of galaxy formation. And now you're starting to see a spiral disk rotating around. The stars, as they're rotating, are moving at more than 200 kilometers every second. Our sun is moving through space, rotating around the center of our galaxy, 200 kilometers every single second. And you wonder why you get dizzy sometimes, right? So it is, tempting, these objects, these merging galaxies. You can see pictures of them taken with the Hubble Space Telescope, like a little gallery on the left there. It's very common for a galaxy to collide with another one. But let's see what our quarks think of that whole thing.
I do enjoy being in a galaxy, but we have learned that some galaxies out there today are merging with other galaxies. It's an elegant galactic dance.
Over a couple billion years.
But for me, it looks like an accident site or a galactic train wreck, maybe.
Let's watch and see.
So this is a picture of two colliding galaxies. The one on the right, called a penguin galaxy, or the penguin galaxy. There aren't a whole bunch of these that we know of or anything. And then this is called the egg on the left. And then the one on the upper right there, that one, that's actually in front. It's closer to us than these other two. And these two are very close together. This one has done damage. This galaxy, the penguin, it used to be a spiral galaxy like I was showing you, like our Milky Way. But the egg there did damage to it. Let's just have a look at this beautiful image, which is a combination of James Webb Space Telescope and Hubble Space Telescope images. We can kind of zoom in on the penguin, and we can see that there are regions like here. These are regions where new stars are forming as a result of the interaction, and up here as well. And so we're able to see all of this detail. And this is a stream that's drawn out of the galaxy by the passage of this galaxy in this direction past it. So this one hasn't merged together yet, but when it does, it will change that spiral into a bigger elliptical galaxy, and it'll lose its beautiful spiral structure. So the Milky Way, as I said, didn't have that kind of a big collision, but it's going to. There's a nearby galaxy called the Andromeda Galaxy. And about 4 billion years, 5 billion years from now, somewhere in there, it is going to collide with the Milky Way galaxy. It's going to get closer and closer in the sky until we can see it covering a large part of the sky, and then it will collide with us. Happens about the same time as our sun dies, I hate to say, so it's not going to be a good time for us, except actually no harm's going to be done when we collide with the Andromeda Galaxy. So let's see. Here's a simulation of this very thing. And so here is the Milky Way galaxy spinning around, doing its thing. And then over here is the Andromeda Galaxy. It's about the same size as the Milky Way, though it formed a bit later in time. And those two are coming together, and then there's a small galaxy called Triangulum that's in the upper left there. And you see them interacting with one another. They get very warped and distorted, and you see these tidal tails, these tidal streams that come out. New stars are forming in these tidal streams. And then the nuclei of the galaxies, with their black holes, they're coming together to form one. And even the black holes will merge together. That will give off these gravity waves. And what do you think is going to happen to us? Actually, nothing. Because the spaces between those stars are so vast that they don't even graze each other. Not even just the stars, but the planets around them. They don't graze each other. And so everything will be fine. And we will be in a galaxy that we like to call Milkdromeda. I like that word somehow.
Well, okay, I agree. It does look like a bit of a dance to me. And I repeat that the stars and planets, they did not collide with each other during this huge galactic collision because the spaces between them was so huge.
And an amazing thing was about to happen to us.
I have to admit, it was amazing to finally become a star.
And we were part of something so beautiful.
So stars form in regions like, these are real, honest-to-goodness images. Here we see an image of a star-forming region called the Pillars of Creation. And we see it imaged both by the Hubble Space Telescope in the optical light, like the kind we see with our eyes, and we see it with the James Webb Space Telescope imaged in infrared light. Infrared light is like heat. It isn't something we can see with our eyes, but we can still measure it with our detectors. And it allows us to see cooler regions, which is where stars collapse and then eventually heat up and form. So zooming in on this image, this is a real image, and this is a visualization of it, but it's just using the real data that the telescopes obtained. We see right here is a region where stars are forming. This is being able to look into that region through the infrared light that it's emitting. Here's a jet that is emitted by a star that's in the process of forming. Again, this is real. This isn't just something that we drew. It's an actual jet from a star that is currently being born. And then we're going to actually zoom down to a region where we can see a very young baby star that has formed on one of these little pillars jutting out of this region, right here. So there it is. So this is a view of the way stars are forming, and the James Webb Space Telescope is producing tremendous amounts of information about that for us. And this is just one of many, many star-forming regions in our galaxy. This is the region around it, and what that region looks like. So it's really quite a beautiful sight. It kind of reminds me of an underwater scene sometimes, rather than something that we would see out in space. So at this point, Hadron is part of a protostellar nebula, which is a cloud of gas from which a star forms and ends up in the core of a star. So the way that that happens is that gravity brings this cloud of gas together, and it collapses. And as it collapses, it gets hotter, and you see at the very center of it here, that's the baby star forming. You see a disk of materials forming around it as it rotates. And it's in a disk like that that planets can form. Okay? But our proton is actually going to end up in the very core of that star. And you might say, oh, that's ridiculous, that something in your brain would be in the core of a star. But I have news for you. Everything in your brain was in the core of a star. It's the only way that you can make carbon, oxygen, nitrogen. It's the only way these things can be made. You literally are made of stuff that was once in a core of a star.
So finally, we were doing something interesting.
Yeah, we combined with another proton and well, it became a neutron. Poor Ed.
And then proton joined and we became helium-3.
And then we joined with another helium-3 and became helium-4.
I remember being so glad I wasn't in one of those two protons that left the nucleus.
Actually, it was more stressful. It looked something like this.
Okay, so here's a collision on the top here between the two protons. They collide together. They emit energy. That energy is what makes the star shine. Neutrino goes off, makes a heavy proton. It's called deuterium. Another proton joins, crash together, make helium-3, which has two protons and a neutron. Same thing happens down here, same identical thing. Photons are produced, that's the energy that comes from it. And then these two heliums collide together, two protons shoot off, and then the other four join together. So that's what Lena said. She's glad that she ended up in the helium-4, okay? But not for long. That's just a depiction, though. When he said it was stressful, it meant something more like this. So here are the protons colliding. Oh, are they going to collide or not? Yep, converted to a neutron. And then here comes another. And we have our helium-4. Things went further for these three, because 3 helium-4 atoms collided together. If it was just 2 of them, they won't stick together. So it has to be 3. And when the three come together at the same time, here comes the other one, it'll hold together because carbon-12 is very stable with those 12 particles. And they became part of a carbon nucleus.
Talk about stressful. There we were, finally in a star, and then the big blast blew us out into who knows where again.
You mean the supernova? Well, without them, there would be no gold. Don't you like gold, Lena?
I mean, I do, but it wasn't right for our lives, you have to admit. Something like this, maybe?
Whoa. So a supernova is a very violent explosion. It does leave behind a neutron star or a black hole, a very dense dead star at the center, but it spreads the material out over large regions in space. It obliterates the system of planets that might be around that star. And it mixes with all sorts of particles from other supernovae that occur all over our galaxy. You probably contain material from 10,000 different stars that went supernova.
That was a hard time, I agree. The supernova remnant was beautiful.
Yeah, but we did wonder if we would ever be part of another star. Little did we know
That we would end up on as part of a planet.
and almost a part of life.
So Ed Salpeter, who Anand mentioned in my introduction, my mentor at Cornell, worked with Carl Sagan for a time to think about what kinds of life could exist in different conditions. And the idea that they came up with was that a planet like Jupiter and Saturn could have a very different form of life than a planet like Earth would have. Since Jupiter is a big gas giant, it would have to have life that could survive in just a gaseous atmosphere. And they came up with the idea of hunters, sinkers, and floaters. Okay, and they actually kind of drew a picture of what they think that the life looked like, and it was a whole ecosystem that they came up with. And of course, now people do much more sophisticated research on astrobiology to try to see what kinds of forms of life could develop, but it's still possible, even to this day, that planets like Jupiter and Saturn could house life something like this. And so we're just going to say that this time our three quark friends are in a Jovian-type planet, a planet like Jupiter, not our Jupiter, but a Jupiter-like thing around another star that is a little bit more massive than the sun, and they're in the atmosphere of that planet. And they are actually breathed in and out by one of these aliens.
So it breathed us in and breathed us out? It didn't like us.
It was close, and then back we were into the atmosphere.
Yeah, it wasn't long after that when we were swept away again.
True.
Swept away to our final resting place.
So this star, when it died, didn't have one of those violent supernova explosions. Instead, it ejected its outer layers as its core was collapsing. That process creates something called a planetary nebula. And they're really pretty, and they're different from each other. These are real images taken by a Hubble Space Telescope of planetary nebula. And the differences between them arise from sort of how the gas is spread out around that expanding star. And you see at the centers of most of them, you see white dwarf that's left behind, like that's the dead star that's left behind at the center. So one of those is actually going to form when our sun dies. And will just look like that, our region of space. This is a little video illustrating what a planetary nebula looks like. And this is one that was modeled to look like a real observed planetary nebula. So you see it's not just that great explosion, but rather less dramatic sort of a thing. And it makes something called the Eskimo Nebula with its white dwarf star at the center. And then we're going to zoom back out and just have a look at it. Here we go. Okay, so then what happened?
And that was that. We were a carbon nucleus out drifting into the space again.
And we made it into the proto-solar nebula this time.
And we made it to the Earth.
And after more than 4 billion years, again, finally, into a living creature.
So again, there was one of these spinning clouds of gas. And this time it's called the proto-solar nebula, not the protostellar nebula, but the proto-solar nebula. And it is rotating around, and gas is condensing into planets. And one of those carbon atoms was our special carbon atom that contained these folks, and that is the one that came to Earth. And it was absorbed into a plant from the air, and it was eaten by a dinosaur. And it was in a part of the body until its death of the dinosaur. I'll let them tell you which part of the body of the dinosaur that was.
Yes, she was a small quellosaur. She ate us. And eventually, we made our way into her heart.
Literally, we were in her heart. I hear people out asking, if dinosaurs could feel love, there is no question.
Yeah, it was going so well with the bell and bow. I have to say that the asteroid was the worst thing that happened to us.
Yeah, it was really hard, wasn't it? I know. I mean, a loving couple of dinosaurs, and asteroid comes down, hits the Earth, cloud of soot goes up, makes the atmosphere dark, sunlight can't get in, and they just didn't make it. None of the dinosaurs did, really. So, Hader went back into the soil again.
It was a long time, more than 65 million years, before we ended up in a living thing again.
Yes, we were lucky to be absorbed into that apple.
And lucky to end up in that very apple that Jane's mother ate.
And to make our way into baby Jane's brain.
And here we are giving this presentation about ourselves.
Yep, that's what happened. Because if you think about it, where did all the stuff in your body come from? You have to breathe it in or eat it or something as you grow. It came from somewhere.
We will only be here for a little while, though.
That is true, but if we were not here, we wouldn't know who we are and all the places that we have been.
You're right. But also, if we weren't here along with all others, then Jane wouldn't know these things.
Yeah, so you see, it's amazing. And no, I don't know what the purpose of all of this is. Yeah? But there is a purpose, and it is more than what we know.
You are right, Harold. Jane should feel good about the person she is. And I think she would feel even better if she had some more ice cream right now.
Yeah, so isn't it amazing that our brains are just at this moment in history, out of 13.8 billion years, that our brains are just developed enough that we're able to grasp this whole story of how we came to be. And we're only here briefly, but I like to believe that if this can happen, then anything can happen. And I think that that should give us all hope. And so I'd like to thank you for your attention, and I hope you enjoyed our little story.
So we also are happy to have Saurav Mopia as the blue and red quark, and myself, Samir, as the green quark. We are at the end of the session, but if there are any questions for Jane about this talk, you're welcome to raise your hands. We'll come to you with the microphones.
Well, wait, I thought the quarks had to answer the question.
Well, we are part of you, so you can do that.
Okay, you're right, exactly. Okay, they're going back into their human forms.
Nice talk. I have one, technical kind of atomic level question. Question is like, can you differentiate between Haider and Lina and Jay was there. So can you differentiate between atomic hydrogen and organic hydrogen?
Atomic hydrogen or?
Atomic hydrogen in space. Can you differentiate that with organic hydrogen? Are they same or they are different?
Atomic hydrogen or?
Atomic hydrogen in space, in the star formation. So that is atomic hydrogen I'm saying about. And organic hydrogen, which is in living creatures, in biology, in living
No difference whatsoever.
Okay.
A proton is a proton is a proton. It's just two up quarks and a down quark. There's no difference between one up quark and another quark except for its color, right? So,
Okay.
No difference.
So, it is on the atomic level. So is there a difference at the compound level, compounds?
Not at all.
Okay.
Hydrogen is hydrogen.
Thank you.
Yeah.
Good evening, ma'am. Thank you for this beautiful talk. Yeah.
There, yes.
So in the beginning of the talk, you said that more protons were formed in the beginning of the universe than neutrons. Why was that? Like, why did that happen?
Yeah, neutrons are not as stable, and they decay into protons. They're a little heavier, and so they're just not quite as stable. And so it's a matter of timing. And that's sort of how we know when the events occurred, because we know that we have 25% helium. That means that the number of neutrons that must have survived must have been exactly the right amount to make that 25%. And that can be calculated, and it was calculated sort of before these things were measured, which is part of what gives us faith that this expanding universe Big Bang theory is true. Yeah.
Thank you, ma'am.
Others, please just keep your hands raised.
Hello. While listening to your lecture, what I saw was that in the beginning, it looked a little bit more chaotic when the universe was forming, and then it kind of settled down. How do I look at it from the perspective of entropy?
So entropy increases with time, as you know. I mean, you can't.
But it looked as if it was much more chaotic at the early stages, and it became much more settled afterwards. So how do I correlate it with the actual entropy that I understand from the universe's perspective?
We create order, but only in little pockets of order, but overall the amount of disorder is increasing. I see what you're saying. And entropy has been a thing with me since I was like 11 years old. I used to ask all my teachers, I think entropy must be a dimension because we need the amount of entropy to describe something just right, like we need the dimensions of space and time. And they just said, why don't you go to lunch or something, and got rid of me. So I guess I have to do that to you as well. I mean, there's no way. You have to use energy and borrow energy to make something more ordered. But I see what you're saying, and I think my answer was not very good to that question, so I have to think about that a little more.
But still, thanks.
Yeah.
Good morning, ma'am. Good evening, ma'am.
Sorry, it's very difficult to tell where the person is.
So as you said that gravity are a favor of time, and like we have studied very much about protons and neutrons, but what about time? Like we don't know anything about time basically. Everything depends upon time, but we don't study about it. So how does time exist? What is it?
It's a dimension like space, and I think time is special because there are 3 spatial dimensions that we experience on a daily basis, but it's also believed that there are other spatial dimensions that are smaller in size than the 3 infinite dimensions that we know of in space. And those dimensions are sort of superimposed on us such that we're experiencing them now without even realizing it. And it's sort of from those dimensions that I think that expanding space must be coming from. And when it comes in, it has this thing called dark energy that makes the universe expand faster and faster than it ever did, and we don't know what that is either. So what is time? I mean, there is an interchange. There are similarities between space and time. The Einstein's special theory of relativity, sort of tells us that. It's one of the things that gives me hope somehow, that we don't understand time. I mean, I'm a big fan of immortality. I've learned recently that some people aren't, but I really am. I want to live forever. I think that I would keep finding things to do, and I want to believe that there's something more there. I don't even know if it relates, right? But there's this thing called the many worlds theory of quantum mechanics, which actually says that with incredible physicists, that I know, think that this could be true. I don't have the expertise to make a scientific judgment about it. I just like the idea of it. But it says that every time that there's like a decision point, that a new universe breaks off in these extra dimensions. And that sort of everything that could happen, happens. And that somehow means, I mean, to me, like, time means something different then. I don't even quite understand. And I'm writing a video game now with a couple of my colleagues where we are having freedom to travel through time. And we have to watch, that we have stable time loops and everything. But, if you can travel through time and live at all different times, and you could, I mean, we're learning to do things like plant portions of a brain into a supercomputer. Like literally scan every aspect of a brain. We can do a fraction of a mouse right now. but it's the size of the computer that limits that. We may be able to scan our brains, put them into computers, and preserve our consciousness for eternity, or for as long as the universe is around. But was the universe created? And if it was created, if there's nothing before that expansion began, then well, what was there? I mean, it's just like, it's amazing that we have a universe at all, but we can't really imagine not having a universe any easier, right? I mean, it's just incomprehensible. That gives me hope. So I don't know, but I think you're right that time is a big part of it, and I hope that people will come to a better, more satisfying understanding of time. You know,
thank you.
That's my answer. Long-winded, but.
Yes, but we still have limited time this evening, so
just have
last
a
two questions. We'll take last two questions. Yes,
so in the timeline that you talked about in the early universe, like, can you pinpoint the time at which like the dark matter and dark energy would have been created?
The dark energy started to enter our universe from other dimensions right when the expansion began. We don't know what it is. It's some kind of a field in empty space, so that space can't really be empty. And it may be that it came to be as part of what's called a phase transition. A phase transition, not like, I mean, it's analogous to between ice and water or something, but it's when forces were unified together. So let me describe that just briefly. I described that there were four forces. And early on, where there was so much energy available, the difference between the particles, the gluon, the WZ bosons, the graviton, the photon, those differences weren't important, and all the forces acted in the same way as each other. And then the universe expanded, that changed, and that change could give rise to energy and expansion or something like that. And so it's probably somewhere in there where this is for the dark energy. It's somewhere in there that it would have emerged at around maybe 10 to the negative 35 seconds, so 0.00034 zeros and a 1 seconds. Dark matter, we don't know what dark matter is. It's some kind of a particle, I suspect, that we just don't know. We haven't discovered it yet. We could discover it next week. And then it would be, oh, we've discovered the axion, okay. And that would have been created as antiparticles annihilated, and those would have been left over from that process. So dark matter isn't as mysterious to us as dark energy, except there are scientists who are researching and think that maybe dark matter doesn't work in the way that we think it does. So I give that caveat. It's not too many that think that, but there are some credible people who think that.
Thank you.
Yeah.
What would eventually happen to the trio when, the expansion of the universe basically dominates gravity?
Yeah, so in our new game, what we're saying is that there's increasing dark energy, which is a possibility. We don't know yet what dark energy is going to do. That means that in 20 billion years from now, if that happens, Andromeda is the only galaxy that we will be able to see, because so much space will have come into the universe between us and the other galaxies that there wouldn't have been enough time for their light to go through that much space to reach us. Then, within a billion years of that, the Andromeda will tear apart. What stars are left from the very diminished supply of gas, there'll be little red stars, they'll pull apart. And then even those stars will come apart. And then, I guess, even our friends will finally part ways. So what we need to do is to be sure that we're able to time travel by then back to an earlier time to sort of loop through and live it all over again, right? It's probably more likely that dark energy will continue in a more stable form, which means that that same thing will happen, but it'll be more like 100 billion years in the future. So it's interesting, though, that it could all come to an end in about 20 billion years. We've been around 13.8. It ends in 20 billion. And here we are right now. And how long are we going to be here? You know?
In this little blip of time that we are here, we thank you for showing us this lovely viewpoint, showing us how the human quest for answers can be so full of beauty and almost poetic as well. So thank you so much again, and we had a great time.
Thank you.
Thank you all for being a great audience. I know you're spellbound. We don't want to leave here after such beautiful visuals. The evening is over. I regret announcing it, so thank you all for being here. We end the program here. We hope to see you again in our next talk. We will have our Foundation Day on 29th of December. It will be a talk which will be announced. So please keep a lookout on our social media. And we hope to see you again in some other event. Okay, good evening.